Welcome to the Ladhe series, Episode 1, The Quantum Threat to Digital Signatures. Today we will set the stage, why every certificate on the internet is on borrowed time, and why hash-based signatures are the conservative answer.
Today's web runs on RSA and elliptic curve cryptography. Every HTTPS connection, every signed software update, every banking session, every authenticated email, all rely on one of these two families. Both are based on hard math problems. RSA relies on factoring large semiprimes. Elliptic curve cryptography relies on the discrete logarithm problem on a curve, on a classical computer. Both of these are believed hard.
Then in 1994, Peter Shor changed everything. He published a quantum algorithm that factors integers in polynomial time. The same algorithm also breaks the discrete log problem. What this means in plain language, on a sufficiently large quantum computer, RSA and elliptic curve cryptography collapse from hard to easy, not slower, not weaker, broken.
And here is the catch. Adversaries do not need a quantum computer today. They are recording encrypted traffic right now, to decrypt it later when the hardware arrives. This is called harvest now, decrypt later. Signatures have an even more pointed problem. A certificate issued today may still be valid when a quantum computer becomes available. A forged signature on a long-lived document would be indistinguishable from the real one. The clock is already ticking.
Throughout this series we will follow two characters, Alice and Bob. Alice signs documents. Bob verifies them. If a malicious party can forge Alice's signature, Bob has no way to tell the real document from the fake one. That is the entire stake of this series.
Cryptographers have explored three main directions for post-quantum signatures: lattice-based, including MLDSA, which NIST standardized as FIPS 204, hash-based, including SLHDSA and SPHINCS+, which NIST standardized as FIPS 205, and code-based, like classic Michaelis. All three are believed to resist Shor's algorithm. They make different bets on which math stays hard.
Hash-based signatures rest on the smallest possible assumption, in modern cryptography, specifically, that the underlying hash function, typically SHA-256, is hard to invert even with a quantum computer. Grover's algorithm gives only a square root speedup, leaving roughly 2 to the 128 quantum work. To break SHA-256, there is no new mathematical structure for an attacker to exploit. There is no exotic assumption that might be broken in 10 years. It is the same primitive that already secures almost every other thing on the internet. That is why hash-based is the conservative choice.
And this is where Ladhe fits in. Ladhe is a hash-based one-time signature scheme. It belongs to the same family as Lampert, SPHINCS+, and SLHDSA. It rests on the same security foundation, SHA-256 preimage resistance. Ladhe's contribution is engineering, not new hardness. We use a compact witness built from additive prime decompositions, yielding signatures around 100 bytes, compared to 17 kilobytes for SPHINCS+. Ladhe does not invent new cryptographic hardness. It packages an existing assumption more compactly.
Here is what is coming in this series. Episode 2, The Pure Math, Additive Prime Decompositions. Episode 3, From Math to Signatures. Episode 4, Certificates and X.509. Episode 5, Standards, the IANA Object Identifier, and the OpenSSL Walkthrough. Episode 6, For Cryptographers, the paper, the code, and the Cryptanalysis challenges. Each episode stands alone. Watch the whole series for the full picture.
The paper and the code are on screen. Up next, Episode 2, The Pure Math. One honest caveat before we go. Ladhe is a candidate scheme. Community cryptanalysis has not yet taken place. We recommend using Ladhe as a hedge, alongside an NIST standard, not as a sole replacement. Thank you for watching.
Welcome back. Episode 2, The Pure Math. Today we look at where Ladhe's numbers come from. The core idea is old. It goes back to Goldbach in 1742. What is new is how we use it as a compact witness representation for a hash commitment.
First, Goldbach in 60 seconds. In 1742, Christian Goldbach conjectured that every even integer greater than 2 is the sum of two primes. For example, 10 equals 3 plus 7, or 5 plus 5. 100 has many such pairs. The conjecture is still unproved, but verified for all numbers up to about 4 times 10 to the 18th.
We do not actually need Goldbach itself. We need a small variation. Pick a prime p. Find a tuple of distinct odd primes, in increasing order, whose sum is exactly p. We call such a tuple a decomposition of p. There are many decompositions for any reasonable p. That diversity is what we are going to exploit.
Why specifically an odd number of primes? Pure parity. Odd primes are odd numbers. The sum of an odd count of odd numbers is odd. The sum of an even count of odd numbers is even. Our p is itself an odd prime. So we need an odd count k of odd primes summing to p. In LAD we use k equal to 3, 5, or 7. Different k values give different witness sizes.
Let us look at a small worked example. Take p equal to 167. Here are some valid decompositions into distinct odd primes. 3 plus 7 plus 157, 3 plus 61 plus 103, 3 plus 5 plus 11 plus 47 plus 101, and longer tuples are possible too. Many tuples sum to 167. Any one of them can serve as a witness.
How many such decompositions exist? For real cryptographic primes, the number is enormous. For a 1024-bit p, the number of valid 3' decompositions is roughly on the order of 2 to the 1014th. That is comparable to the security level of pre-quantum RSA, not because finding a decomposition is hard, but because there are so many valid ones for the signer to choose from.
Now the engineering trick that makes Ladhe compact. Take the decomposition p1 through pk. Instead of storing all k primes, we store the indexed pair compression. We pair them up from the start, and since k is odd, the last element stays unpaired. For our example with 5 primes 3, 5, 11, 47, 101, the compressed witness becomes 8, 58, 101, 3 numbers instead of 5. The verifier can do its job from this compact form, as we will see in episode 3.
At cryptographic sizes, this halves the witness footprint. Without compression we would store k full primes. With pair compression we store k plus 1 over 2 numbers. For a 1024-bit p with 3 primes, the raw form is roughly 384 bytes. The compressed form is about 100 bytes. That is the entire reason Ladhe signatures are so small. Compare with SPHINCS+, whose signatures are around 17 kilobytes. Ladhe signatures fit in roughly 100 bytes.
So we have a tuple of primes summing to p, and a compact 2 or 3 number witness W. Where does the cryptography come in? The signer keeps the prime secret. The signer publishes p and the SHA-256 hash of the encoded witness. That is the public key. Security comes from the hash. The only way to forge a valid witness is to find a preimage of the SHA-256 hash, and that is the SHA-256 preimage problem. No new hardness assumption. The same foundation as SPHINCS+.
To recap, primes summing to p give us the witness. Indexed pair compression makes it compact. SHA-256 of the encoded witness becomes the public key. Up next, episode 3. From Math to Signatures. We will watch Alice sign a document, and Bob verify it. Thank you for watching.
Welcome back. Episode 3. From Math to Signatures. Today we watch Alice sign a document, and Bob verify it. Then we look at how Ladhe stacks up against the NIST standards, and against quantum key distribution.
Quick recap from episode 2. The private key is the secret tuple of distinct odd primes, summing to P. The public key is P itself, plus the SHA-256 hash of the encoded compressed witness. Now we use these to sign and verify a message.
To sign a message M with private key P and the primes, Ladhe does 3 things. First, bind the message to a fresh transcript, using the Fiat-Shamir transform. Second, use the secret primes to construct a witness W that opens the public commitment H. Third, output the signature as the transcript, the witness, and a message tag. About 100 bytes total. No exotic math, no hypertree, no number theoretic transform.
To verify a message and signature against the public key, Bob does 3 things. First, recompute the Fiat-Shamir transcript from the message. Second, check the witness arithmetically. Components must be consistent with P, and the encoding must be well formed. Third, recompute the SHA-256 hash of the encoded witness, and check that it matches the public commitment H. If any step fails, reject. Otherwise, accept.
An important caveat, Ladhe is a one-time signature scheme. Signing reveals the witness W. Anyone who sees one valid signature learns enough about the witness to forge a different message under the same key. Therefore, one Ladhe key signs one message. For many-time signing, the paper sketches a Merkle aggregated construction in section 6. The same idea SPHINCS plus uses. That variant is not yet implemented in version 1.0.
Here it is in action. Run Python Ladhe rs.py demo 5. Key generation produces P, the primes, and the public hash. Signing takes about a millisecond. The signature is 104 bytes. Verification takes about half a millisecond. And tampering with the message produces a clean rejection.
Now the comparison. Here is Ladhe v1 alongside MLDSA 65, FIPS 204, and SLHDSA 128S, FIPS 205. Ladhe signatures are roughly 100 bytes, compared to 3,000 for MLDSA, and almost 8,000 for SLHDSA. Ladhe public keys are about 36 bytes, compared to 1900 for MLDSA, but, and this matters, Ladhe is one time only, and has no community cryptanalysis yet. The NIST schemes are many time and extensively studied.
Where does Ladhe win in version 1? Signature size, about 33 times smaller than MLDSA, and 78 times smaller than SLHDSA. Public key size, about 54 times smaller than MLDSA. Code simplicity, no number theoretic transform, no hypertree, about 600 lines of auditable Python, pure software, no hardware accelerator required, and the same security foundation as SPHINCS+.
And we owe you the honest version 2. Where does Ladhe not win in version 1? It is one time only. The many-time variant is sketched in the paper, section 6, but not yet implemented. Key generation is slow at high bit sizes, around 90 seconds at 3322 bits. It is not NIST standardized. That process takes 5 to 10 years, and there is zero community cryptanalysis yet. That last point is the biggest. Use Ladhe as a hedge alongside an NIST standard, not as a sole replacement.
What about quantum key distribution? QKD and Ladhe are not really competitors. QKD distributes symmetric keys between two parties, using quantum physics. Protocols like BB84. It needs dedicated hardware, fiber or satellite links, and works only over limited distances, roughly 100 to 300 kilometers in fiber. Each node costs tens to hundreds of thousands of dollars. Critically, QKD does not authenticate. It actually requires a digital signature scheme on top, to prevent man-in-the-middle attacks.
QKD and Ladhe are complementary, not competitive. QKD distributes a symmetric key between two endpoints. LAD, or any signature scheme, is what proves the right parties are on the line. In a real QKD deployment, you still need a signature scheme to authenticate the classical channel that QKD depends on. LAD could play that role. Different tools, often used together. We are not competing with QKD.
We now have working signatures, sized, and compared honestly against the alternatives. Up next, Episode 4, Certificates and X.509. Signatures alone are not enough. Bob needs to know that the public key really belongs to Alice. That is what certificates are for. Thank you for watching.
Welcome back. Episode 4, From Signatures to Certificates and X.509. A signature proves the holder of a key signed something. A certificate proves who that key belongs to. Today we close that gap.
Imagine Bob receives a signed purchase order. He can verify the signature against a public key. But how does he know that key really belongs to Alice? Without an answer to that question, any attacker could generate their own LAD key pair, sign a forged purchase order, and call themselves Alice. We need to bind keys to identities.
A certificate is a small structured document. It contains the subject's identity. For example, common name Alice in procurement. It contains the subject's public key. For LAD, that is P and the hash H. It contains validity dates. And critically, it contains a signature from a trusted certificate authority, the CA. The CA's signature vouches for the binding between the identity and the public key.
Meet Alice, Bob, and the CA. Acme CA is the trusted authority. It issues certificates for Alice and for Bob. When Bob receives a signed document from Alice, he checks: is Alice's certificate signed by Acme CA? Is the document signature valid for the public key in that cert? Is the certificate currently valid in time? If all three pass, trust transfers from the CA, through the certificate, to the document.
Step 1. Build a root CA. We run LAD cert init CA, name it Acme Quantum CA, and write out the CA certificate and the secret key. LAD cert show inspects the CA cert. It is a self-signed root, valid for the next 5 years.
Step 2. Issue a certificate for Alice. LAD cert issue takes the CA files, and Alice's intended subject name, and writes Alice's certificate and her secret key. Anyone holding the CA certificate can now verify that Alice's certificate really came from Acme Quantum CA.
Step 3. Alice signs the purchase order. LAD cert sign doc binds the signature to Alice's certificate. The output names Alice as the signer, references the certificate, and shows the signature size, about 104 bytes.
Step 4. Bob verifies. LAD cert verify doc takes the CA, Alice's cert, the document, and the signature. If everything matches, verify equals true. Now we tamper. Change 200 to 999. Rerun verify. Verify equals false. The forgery is caught.
X.509 is the universal certificate format. It is what every TLS certificate on the web uses, and what OpenSSL, browsers, and operating systems already understand. LAD ships an X.509 export, so existing tooling can read LAD certificates without any code changes. Run LAD cert 2x509, then OpenSSL X509 text. You see the standard X.509 fields, with LAD's algorithm identifiers in the public key, and signature algorithm slots.
Up next, Episode 5, Standards, the IANA Object Identifier, and the OpenSSL Walkthrough. Those algorithm identifiers you just saw are not made up. They are registered with IANA. Episode 5 explains how, and why it matters for interoperability. Thank you for watching.
Welcome back. Episode 5, Standards, the IANA Object Identifier, and the OpenSSL Walkthrough. Today we look at why an algorithm needs a registered identifier, how LAD got one, and how it shows up in OpenSSL.
What is an object identifier? A node. It is a globally unique number that names a thing in a hierarchical namespace. Some you have already seen without realizing. 1.2.840.113549 is RSA encryption. There is one for elliptic curves, and one for MLDSA65. Every cryptographic algorithm in standard use has a node. Without one, no standard parser can recognize it.
Why does Ladhe need an OID? An X.509 certificate has fields for the public key algorithm and the signature algorithm. Both of those fields contain an OID. Without a registered OID for Ladhe, no third-party tool could parse a Ladhe certificate. As a Ladhe certificate, it would just see unknown algorithm and reject it. An OID is the entry ticket to the existing PKI ecosystem.
How do you get an OID for a brand new algorithm? Through IANA, the Internet Assigned Numbers Authority. IANA issues private enterprise numbers, or PENs, to organizations. Each PEN gives you a slice of the global OID tree. Within that slice you can mint as many sub-OIDs as you need. PENs are free. They take a few weeks to assign, and last forever. This is how every serious vendor, Cisco, Microsoft, RSA, anchors its proprietary identifiers.
IANA assigned PEN 65644 to Les Secure on April 23, 2026. From that we minted 3 OIDs. I'd Ladhe signature for signatures, I'd Ladhe public key for public keys, and I'd Ladhe cert v1 for the certificate format. These are the exact strings you saw in episode 4, when OpenSSL read Alice's X.509 certificate.
OpenSSL ASN1 parse walks the raw ASN1 tree. Run OpenSSL ASN1 parse on Alice's X509 cert. You will see the structure unfold, and you will see 1.3.6.1.4.1.65644.1.1 appear as the object in the signature algorithm slot. That is Ladhe. Standard tool, standard parse, recognizes Ladhe by OID.
For a more human-readable view, run OpenSSL X509 text. You see the certificate as a structured document, issuer, validity, subject, public key, all of it standard X.509, with Ladhe's OIDs in the algorithm slots. This is the same output a network engineer would see for any TLS certificate.
Having an IANA OID is the first step. It is not the last. Right now we have a registered OID and an open implementation. Next, the scheme needs community cryptanalysis. That is essential. Then would come an IETF, algorithm identifier draft, and eventually, NIST evaluation. If the scheme survives community review, we are at step 1. Help with steps 2 through 4 is welcome.
Up next, episode 6, for cryptographers, we will tour the paper and the code, show you the Cryptanalysis challenge generator, and explain exactly what would constitute a break. If you break Ladhe, we want to hear from you. Thank you for watching. Welcome to the final episode, episode 6, for cryptographers. This one is an invitation. Read the paper, run the code, try to break it.
First the paper. Title, Ladhe Signatures. Compact hash-based signatures. From Additive Prime Decompositions. Authors, Shubham Ladhe and Pankaj Ladhe. Available on Zenodo as a peer-reviewable preprint. It contains the formal scheme description, the security reduction to SHA-256 preimage resistance, Civ accelerated key generation benchmarks, a sketch of the Merkle aggregated many-time variant, and honest open questions in section 7.
The code lives at github.com/spalgorithm/le. LadheRS.py is the core scheme. About 600 lines. Ladhe cert handles the certificate format. Ladhe X509 handles X.509 export. Verify.py is a standalone single file verifier. In pure Python standard library, no dependencies. And the demo folder builds a self-contained kit. The code is MIT licensed. Pure Python. Reads top to bottom. Written to be auditable, not optimized.
And here is the Cryptanalysis challenge. Run Python with generate LDP challenge. At any bit size you like. It produces a fresh P and a fresh hash H. Your task: find a tuple of distinct odd primes, with k odd, summing to P, such that the SHA-256 hash of the encoded, compressed witness equals H. We hold the witness. We will not release it. If you find it, you have broken Ladhe at that bit size.
Here is what we know about the attack surface. Generic hash preimage via Grover gives about 2 to the 128 quantum work. For SHA-256, direct prime decomposition search is exponential. In the bit size of P, pair compression collision reduces to SHA-256 second preimage resistance. Side channels are out of scope in version 1, and we flagged that openly. Key reuse trivially breaks the scheme. We document each of these in paper section 7. Read it. Find a hole.
We are committing in advance to what we will accept as evidence of a break, an algorithm that recovers a valid witness from the public P and H in less than 2 to the lambda over 2 work, where lambda is the security parameter, or a forged signature on an attacker-chosen message that verifies under a target public key, without the secret primes, in less than the same bound. Below either bound is a break. Above is not a break yet, but still useful analysis.
Here are open questions we would like help with. Is the witness encoding tight? Compare compression hide structure. That helps a preimage attack. At what bit size does key generation become impractical? Can our sieve and Miller-Rabin combination be replaced with something faster? Is the Merkle aggregated many-time variant secure when instantiated naively? How does Ladhe interact with hardware security modules that lack arbitrary precision arithmetic?
How to get involved. Open a GitHub issue at github.com/spalgorithm/le. Email us at spalgorithm@gmail.com. Comment on the IACRE print post once it is accepted. If you have a cryptanalysis claim, include the witness so we can verify it. We will give public credit for accepted analysis, with attribution as you prefer. We are not asking for endorsement. We are asking for scrutiny.
Where Ladhe's, honestly, a candidate hash-based one-time signature scheme. Same security family as SPHINCS plus and SLHDSA. Compact signatures, around 100 bytes. Working code, X.509 export. And a registered IANA object identifier. Caveats: no community cryptanalysis yet. Many time variant not yet implemented. Recommended uses as a hedge, alongside an NIST standard, not as a sole replacement. Version 1.0. The work begins now.
Paper, code, and contact details are on screen. Thank you for watching the Ladhe series. If you have made it this far, you understand the scheme as well as we do. The interesting work now is finding what we missed. Now go break it.